Right, folks, so we are on to, if you have a copy of the module booklet, we're on to page 17. If you haven't, then you want to find a page that says, I've just realised, a title that makes absolutely no sense at all. So you want to find a page that says, what do plates move? Ha! You need to change that, sorry, to either why do plates move, or what makes plates move. Clearly, I got indecisive about which of those sentences I was going for, and put a complete load of gobbledygook. Sorry about that. Anyway, at least it means you might find it quite easily. So, what do plates move? Please change that title, page 17. Okay, so what we're going to do today is we're going to talk about why plate tectonics happens. So we know it does. We know that there was a whole load of kind of stages to go through in order for that to be proved, and we found out about Francis Bacon and Alfred Wegener and J. Tuzo Wilson and all of these important people, and how we needed to find the mid-Atlantic ridge and we needed the fossil evidence. We know all of that. We're finally moving on to, okay, fine, I accept that. What is it that makes the plates move? And it's fundamentally something called convection. And I've put two just everyday sort of diagrams on the screen for you. Convection happens all the time, everywhere. It's just part of your daily life. So if you are heating something on the hob, so maybe, I don't know, you're cooking some peas in some boiling water, convection happens. If you've got your heating on, either a radiator or maybe a nice open fire, convection happens. It happens in hot air balloons all the time. So hot things rise, they cool and they sink, and you get this cycle, all right? So that happens in the Earth because the core of the Earth is very, 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 very hot. That's still an understatement, even with all of those verys. So the core of the Earth is very, very hot, and it causes convection. So you can see a sort of simplified diagram of that. You might want to add some arrows to the diagram that you've got on page 17 to just kind of show what we mean by convection. And if you think it would help you, you could copy one or both of those maybe into the space at the top of page 17. That could be quite effective. So that's what convection is, and it happens in the Earth. All right, so you've got this current that moves the plates. So we've talked about how the asthenosphere is plastic, semi-solid. It's a solid that has movement. I said to think of it a bit like blue tack or Play-Doh. And I said that that's really important because if it was solid, where does our movement happen? So we have our convection that moves the asthenosphere around, and because the crust is sat on top of the asthenosphere, or I should say, sorry, the lithosphere is sat on top of the asthenosphere. That means that as the asthenosphere moves, so does the lithosphere. And fundamentally, that kickstarts all of our plate tectonics. So, I was rather pleased. Can we skip some ads? Cheers. I don't know why I'm getting so many of these adverts. Apologies, folks. This is not very long at all.
But the huge molten core contributes something else essential for life on Earth. A way of helping to regulate the planet's temperature. It's a remarkable system. Magma heated by the core rises towards the Earth's surface. As it spreads sideways, the Earth's crust is very slowly dragged apart. This moves the continents, creating the Earth's restless and ever-changing surface.
There, very short, but very effective. Just gives you a sense of what convection might look like. Okay, here are the two bits that might confuse your brain a little bit. So convection, hopefully, is reasonably straightforward. Ridge push and slab pull. These are right at the bottom of the page. Okay, so we've established that there's convection happening. We've established that the lithosphere is kind of floating on the asthenosphere. So if the asthenosphere moves, the lithosphere has no choice but to go along with it. Okay, so you've got your convection current. This is probably what you would currently call a constructive margin. I am going to try, if at all possible, to give you an alternative name, but more on that in a bit. So a constructive margin, which is where two plates are moving away from each other, and as they move away, you get magma coming up in the gap underneath, and you get your volcanoes and everything else. So it's constructive because new oceanic crust is being constructed. Okay, so the convection is coming up underneath those two bits of crust, and they are being pushed apart. So the convection is the kickstarter, but then you've got ridge push, which is going to help maintain that movement. And then here is possibly the surprising one, slab pull. So we actually now think that slab pull is probably more important than ridge push. If you look on page 17, it actually says ridge push only contributes about 5 to 10% of the movement. So ridge push has a part to play, but it's quite a small part. This one, slab pull, seems to be much more important. Now, I've got a bit of a bizarre way to try and explain it to you, which involves one of my stunningly beautiful diagrams. Okay, let's say you linked arms, how many have I drawn, with 6 of your friends, and one person at the end of the chain decides to start running downhill. If you held on to each other's arms and linked and stayed together, it would have the effect of beginning to drag people down with them. And that's essentially what slab pull is. Because this bit of the plate has started to be subducted, and if you're not completely sure about what subduction is, by the end of this week you will be fine, because we're going to be talking about it a lot. Basically, it's that the plate is being pushed down into the earth and melted. Once that process has started, what that plate is going to do is it's going to pull the rest of the plate behind it along. So you might, I don't expect you would ever link arms with 6 of your friends and start running downhill. It's probably not, well, you certainly couldn't do it at the moment, could you, with social distancing? And I don't think it would be the most fun you've ever had, even in normal times. But hopefully that analogy just gives you a sense that what the plate is doing is it's pulling the rest of the plate behind it and pulling it down. And it is believed that that process is much more important than the ridge push. Strange, but kind of true. So there's 3 things to know about plate movement. You've got these convection currents going on, all because the core is hot, the asthenosphere has movement, and the lithosphere is kind of floating on top of the asthenosphere. So if that moves, it moves as well. You've got ridge push and slab pull. Okay, so that's how your continents and everything move apart. But obviously, if the Earth's crust is divided into plates which move, that is our theory of plate tectonics that we sort of started with, clearly these plates are all moving towards each other, away from each other, past each other, and hey presto, ladies and gents, we get plate margins. And plate margins are the key to the rest of the module, really. If you can get your head around your plate margins, the rest of the module is going to be relatively straightforward for you. There's a slightly nicer map, a bit more detailed. We've given you a map on page 18 that you may wish to add notes to. some students actually printed that one, the one that's on the screen at the moment, in colour. They found that really helpful to kind of see how everything worked together. And it's quite nice because it shows you all of the different plate margins are colour coded. You've got the hot spots shown. So yeah, if you've got the printer ink and the facilities, a colour copy of that might be quite useful. So the rest of this week is all going to be plate margins. They are on, well, they're not actually. There's space for notes on pages 19, 20 and 21, but some of you might want to use just ordinary paper. Some of you might want to do this digitally. You might want to do a PowerPoint, revision cards. I'm really not fussed, but we want really good notes on plate margins, please. Because as I said a couple of minutes ago, if the plate margins make sense to you and you're happy with them, the rest of the module is really quite straightforward. So please put lots of time and energy into these. I'm going to do a video on every single type of plate margin, so you could take most of your notes from those, but equally, if you've had enough of listening to me and you want to freestyle, that's fine too. It's the detail that's important, okay? So on page 19, it says, for each one, you must, and I've capitalised that because it's so important, an annotated diagram, hazards and the landforms found there, key terms and information about the example listed. Right, why do we want diagrams? Because one of the things that we will tell you more about when we really start practicing our essay writing is they love a diagram in the middle of an essay, your exam board. I think geography is quite a visual subject anyway, and just being able to drop in a plate margin diagram really is going to help you stand out from the crowd in terms of your knowledge, which is always a good thing. Yeah, diagrams are good. Okay, and plate margins make really fantastic diagrams. So we definitely want a diagram. A hazard, what I mean by the hazard is, does each plate margin have volcanoes? Does it have earthquakes? Does it have tsunamis? What things at that plate margin could cause damage and kill people? Because every margin is slightly different. Some of them have volcanoes, some don't. So hazards. Landforms, what does the land look like? What things are you going to find there? Key terms is fairly obvious. Information about the example listed. These are sort of name drops almost. I don't know if they're big enough to be called case studies. They're just name drops really. So if you were talking in an essay about a particular kind of plate margin, it's nice to be able to say an example of this kind of margin is the Himalayas, for example. So if you just know a little bit about each of those examples, that would be really, really good. And if I can just remind you, if you get stuck on anything to do with margins, just send questions to Nick. Send them as soon as they pop into your head, because otherwise, if your memory's anything like mine, it'll be gone forever. Send Nick an email, nickw@richhewish.ac.uk, and then on Mondays at 2 o'clock he will work his way through the questions he's got. All right, so don't be embarrassed to do that. So the last thing I'm going to do in this video, which is my sort of little introduction, I'm just going to sort of give you a sense of what you're in for. Now, it would be lovely if we can use the words in the dark blue bit of the table: divergent, convergent, conservative. If you get really stuck on that because you learned constructive and destructive so much at GCSE that they're just in your head, it's not a disaster. It's not the end of the world. But if we could possibly use the terms in the dark blue, that would be really good. So we've got divergent plate margins, and what we mean by diverge is to move away, to split apart. So divergent plate margins, the plates are moving away from each other, and we've got two that we're going to learn. You can get divergent plate margins under the sea, and you can also get them on land. So we're going to work our way through those. Convergent plate margins are the exact opposite. So if you converge, it means you move towards something. And in a convergent plate margin, you've got the two plates moving towards each other. Because we've got oceanic and continental crust, that means there must be 3 types of convergent margin, depending on whether it's oceanic crust meeting another bit of oceanic crust, whether it's continental meeting continental, or obviously oceanic meeting continental. So we've got 3 of those. Then we've got conservative. I am definitely least worried about what you call these. Some people call them transform margins. Some people call them strike slip. I would say any of those are equally fine. Conservative is my preference, but that's fine. And a conservative margin, the plates are not moving towards or away from each other. They are moving past each other. So we only need to learn one. So look, here in the mid-Atlantic ridge, which we've talked about, you've got the arrows moving away from each other. So that is a divergent margin. Here we've got the arrows moving towards each other. So that's a convergent margin. And here, this is probably quite famous, the San Andreas fault, the arrows are going in opposite directions. So as I said, some students quite like to print this out in colour if you've got the opportunity to do that. If you can't do it yet, don't worry, but this sort of is quite a nice reference point. Or you could get your colouring pens out and colour in page 18 if that's a much cheaper option, I would suggest. So what I'm going to do for the rest of the videos this week is I'm going to go through each of those plate margins. You can either take notes from the videos for your revision notes, or you can do some internet research or whatever. But this week's mission is to find out about every single type of plate margin in as much detail as we can. We also, that I've not listed them on this page because they're not margins, but we are also going to talk about hot spots. You may have noticed them on here. They're the little purple things. They're not a type of margin, but they make sense for me to explain them with margins. And there's a space for notes about hotspots on page 21. Okay, so for the rest of the videos this week, that's what we're going to work through. Just remember to send questions as they pop into your head. All right, thanks everyone.